As was said, Corbin Lewis presenting a new measurement approach to determining sand dune width and spacing trends in Titan's Bullet Sand Sea. Unfortunately, this title is slightly misleading, as you will find out soon, and I will explain why. At this time, I'd also like to recognize Brad Bishop, Dr. Radaba, and Dr. Christensen and their efforts. This has definitely been a team project. All right, so my hope today is to take you on a journey that is out of this world, and so we will go to Titan. Titan is Saturn's second largest moon. It is approximately 5,150 kilometers in diameter. That makes it about 1.5 times the size of Earth's moon, and actually makes it a little bit bigger than Mercury. So to give you somewhat of a perspective of the size of the body we're dealing with. The reason Titan has become a body of so much interest is because of its striking similarities to Earth. We see very similar geomorphologies on its surface. It has very similar looking stream systems. However, these systems are filled with liquid methane as opposed to liquid water. Titan is much, much colder and has been compared by some to a much younger frozen Earth. Titan is also shaped by winds that transport sediment. So let's narrow, oops, press the wrong button, sorry if I did someone. Let's narrow our focus a little bit and talk about Cassini and what Cassini has done. So what we're looking at now is a mosaic of images collected by Cassini. Cassini performed its first flyby of Titan in 2004 and has performed many flybys since then, collecting various data. The data that we have focused on for this study are these radar images. Also what I'd like to point out is the intricate surface that we see on Titan, particularly in the equatorial region. We see this lighter region, Xanadu, which is an elevated mountainous region, but then we see these darker areas in this equatorial region, and these are sand seas. All right, so this slide kind of brings together the point of why this is all important. And like I said in the introduction, we see very similar geomorphologies. But before we compare the two, let's talk about how sand dunes are showing up in radar. As we look at this image, we see these dark and light alternating bands. As Cassini sent down its radar signal, the sand dunes themselves absorb that signal, and so we get these dark bands. However, the rougher inner dunes reflected that signal back, and so we get these lighter bands. And so we have this alternating light-dark pattern. So now let's compare these two images. As we know, this is a radar image of Titan, and then on the right is an image of dunes in Egypt. And as we look at these, we see that the dunes in both are long, narrow, and relatively straight. In both images, we are looking at longitudinal dunes. And so it's very interesting that we're looking at very similar geomorphologies, but they are coming about in environments that are in very different conditions. All right, so our area of focus for this study is the Bullet Sand Sea, as mentioned in the title, and it happens to be the largest sand sea on Titan. Its area is approximately 3.3 million kilometers squared, and its volume is in the range of 610,000 to 1,270,000 kilometers cubed. And as we talked about with the dunes we were looking at on the previous slide, the dunes in Bullet are long, straight, and closely spaced. All right. So the margin we chose to use is signified here in green, and this was determined by determining a correlation of dune presence in SAR and near-infrared images. And then you see blue markings on the far left of the image, and these orange markings here. And these represent 2,470 measurements of dune widths and spacings. And they're kind of helter-skelter in blue, but in the orange you'll notice some organization. They're divided into distinct groups which represent 90 kilometer square areas, and measurements within those are every 5 kilometers. And this data was gathered quite tediously in a program unfortunately known as ISIS, and was then put in ArcMap, and using the near analysis tool, we were able to determine their distances from the dune margin. Alright, so it may still be somewhat unclear as to what exactly we're measuring, and so that's what I'd like to address on this slide. Once again, here's the dunes we're seeing in Bullet, these light dark bands, and then here's a diagram to illustrate that. So ideally we would be measuring from crest to crest with dune spacing. However, due to the resolution of these images, that is quite difficult. So instead we use the light dark boundaries that we see between the inner dunes and the dunes. So for example, measuring the dune spacing, if the direction to everyone's left is north, then I would measure the northern boundary of this dune, and then to the northern boundary of this dune. And then to measure the width, be the northern boundary of this dune and the southern boundary of that dune. And that was done many, many times. All right. So a strong trend that we do see is comparing the width of dunes to latitude. And as you see in this diagram, the width tends to decrease with increasing latitude. We see a maximum dune width at about 7 degrees south latitude, and then it decreases from there. However, this wasn't the trend that we were focusing on, so we'll spend most of our time discussing the other trends. Here's a scatter plot of all of the data gathered. The x-axis is distance from dune field margin, and the y-axis is the width of the dunes. And we were hoping to see a clear trend, either increasing or decreasing in dune width as we moved away from the margin. However, we didn't find that. Instead, what we found when we displayed the data in this way is a decrease in range of widths as we moved away from the boundary. So we see a much larger range here as opposed to our furthest distance. Also, an issue we discovered as we looked at this data is we realized we had a lot more data in our first interval of 0 to 100 kilometers as opposed to the rest of our data. So what we decided to do was divide this data into 100-kilometer intervals and compare it percentage-wise within those intervals, and then compare all those intervals. So this is our first interval, 0 to 100 kilometers, and what we see is about 40% for 0.5 to 1 kilometer, and then 1 to 1.5 kilometers. As we move on, we see a general increase in dune width. Notice how 0.5 to 1 kilometer width is far less, and our dominant is 1 to 1.5. And we see that same result through the next couple intervals. However, when we get to our last interval of distances greater than 400 kilometers, once again, we're to a smaller dune width. So we've seen this increase as we move away from the the sand sea margin, and then as we get to our farthest interval, we once again see a decrease in dune width. And here is a graph comparing all of those, hopefully making it easier to see that trend. All right, so let's talk about, in conclusion, what all of this means. On Earth, we see examples of narrow dune widths, and that is associated with a high sediment supply. And so if we take that and apply that to the two different displays of data that we looked at, so let's first apply that to the scatter plot. When we apply that to the scatter plot, we're seeing these differing ranges, or a decrease in range as we move from the margin. So we can interpret that to mean that there's less variation in sand supply as we move further from the margin, because we're seeing this wide range in dune widths. And so we're having a more constant supply. However, if we apply these Earth examples to what we see on Titan when we're looking at our column charts, we're seeing large sediment supply near the sand sea margin, and then that sediment supply is decreasing as we move away, and then once again increasing as we get to our furthest distance. Personally, the scatter plot makes the most sense to me as far as the data, as far as how all that data shakes out. it seems to be clear to me. I feel that perhaps the trends we're looking at that are displayed by the column chart may still be somewhat altered according to the data that we have. And I think collecting more data would clarify those trends. And so that is something we plan to do as we move forward. As we're studying all this, we're hoping to better understand processes that shape Titan's surface, as well as we're hoping to better understand how we're gaining such similar geomorphologies under such different conditions. So moving forward, you'll see in this image we have these blue outlined areas. These are non-dunal areas within the sand seas, and they're called Inselbergs. We plan to include these in our analysis of data in the future to see how those influence our width and spacing trends throughout the sand sea. Like I said, we plan to add more data, hopefully to see clearer trends. And then the new method, which is spoken of in my title, we finally got there. Unfortunately, with some hangups, we weren't able to include that in the project, but what it will allow us to do is, using ArcGIS, we'll be able to measure from polyline to polyline and collect measurements every 500 meters along a dune. So instead of having to resort to a system where we're picking 90 square kilometer areas, hopefully we'll be able to go through and measure essentially the whole sand sea and have very thorough data sets. And then we won't have this doubt of, oh, is our data unbalanced, or things like that, and we can move forward confidently. So, thank you.
How do you, when you go in and measure your dune inner dunes, what level of pixelization you got? How do you pick your margins? You know what I'm saying? Here's the dune, here's the end of the dune. Mm-hmm. What are you looking at? I mean, how close are you zooming in on this, and how are you picking this, and then how are you measuring it? How do you know, at each, these different latitudes, you got different scales, how are these calibrated? Are you measuring right on a geosphere using ArcGIS or MapMaker Pro? How do you do that?
Great question. So up to this point, we've been using ISIS. That has been the big problem holding back our new method, is getting a projection. Getting a projection that works in ArcGIS. And we feel that we've finally found one that will work for that. Dealing with those distortions that you see with projections and things like that, so getting one that actually works. But what we're measuring from are the light-dark boundaries between.
I know that, but I'm saying when you zoom in, I mean, that looks like pretty dicey data, you know what I'm saying?
Yeah.
So absolutely. When you zoom in, where are you picking that margin? You zoom in and you say pixelates and you say, well, I'm going to call it this percentage of gray, or how do you do that?
Yeah, so when we're zooming in,
to be consistent each time. That's what I'm asking.
Yeah, so we're dealing with the resolution is about 350 meters per pixel. And it is difficult to be totally consistent. So essentially it's more or less eyeballing that contrast. And as you zoom in, the contrast is pretty clear. So, especially right along that light-dark boundary between the inner dune and the dune.
Have you thought about using any software to go do this for you? Just go mine it out, like geography. You have some mining, some of this software that goes in and mines out the data, so you're not biasing with your information, with your I don't know, your preconceived notions and stuff. You know what I'm talking about? Mm-hmm. So you say, here, go look at all these things, and you throw it into the computer. Do you want to do that? Has the computer pick it?
There have been attempts kind of like that regarding figuring out the sand sea margin as far as individual dunes. I'm not sure how much thought's been put into that.
Other groups are doing that. I think the problem is that there are biases also with
you code it in.
Yeah, and so
but then you can just do huge areas, right? I mean,
yeah,
quickly,
essentially, and there are some who are doing that, but then relating that to a dune length and to a so by actually tracing down a margin, you get a full length of the dune. So we're taking a labor-intensive approach. I think that there's more to be gained in what we're trying to do by keeping eyes on it. But I think you're right. We're thinking about going across them and try to get some light dark peaks and troughs, and that would be something interesting to do.
Yeah.
So Chris Savage looked at dune spacing from latitude, kind of a latitudinal approach. And now you're looking at it from an outside-in approach. And I think that's really cool. And I think that your implication is that you're going to have more forcing, variability in the forcing mechanisms of how dunes align and the width spacing at the edges of these sand seas than in the interiors. It'll kind of get ordered, more ordered as you go into. And I really think that's an interesting thing to work with. Is that true? Is that what I'm gaining out of kind of your approach here?
Yeah, that's the conclusion I'm currently at.
Yeah.
We're seeing more variation closer to the margin.